Hello, everyone. Welcome to the Temporal Graph Reading Group today. We are very glad to hold Maciej from ETH Zurich, and he will be presenting his recent work from log 2023 on the higher order dynamic graph representation learning with efficient transformers. And more on the speaker. Maciej leads the research on graph computations and large language models at the Scalo Parallel Computing Lab at ETH Zurich and the ETH Future Computing Lab. He also works on network topologies and other aspects of the high-performing computing landscape. He has published more than 50 top conference and journal papers, as well as competitions for the Best Student Award of Poland and the Google Fellowship in Parallel Computing and so on.
Yeah, we can maybe skip that and just
we're
get
gonna
to
skip
something.
all the awards.
Yeah, let's just get to something more
questions.
interesting. Yeah.
So I'll hand the mic to you. Yeah.
Yep. Thanks a lot for the invitation. Nice introduction. So yes, I'm Maciej. I lead a couple of efforts in SPCL, Scalable Parallel Computing Lab at ETH and EFCL. And I would like to present actually not just the results from our log 2023 paper about HOT, but really a couple of other things, because this paper that you mentioned from log is basically a small part of our larger pipeline for mining and analyzing different aspects of dynamic/temporal graphs and doing a couple of other cool things. So let me get to it now. In general, what I'm interested in, let me maybe first quickly introduce my overall interest is basically irregular and sparse computing. So that means that I'm usually interested in different objects, entities that we can model using either graphs or sparse matrices, and doing efficient computations on these things, right? So that means that I'm working on a couple of interrelated domains. These days, it's a lot about LLM ecosystems and agent infrastructures, which actually can also be nicely modeled with these objects, but that also means a lot of works into generative AI training and inference, into GNNs and overall graph representation learning, graph databases, different forms of graph compression and summarization, pattern matching, classical parallel and not only parallel graph algorithms, temporal streaming and then dynamic graphs, and a couple of others, right? So we all know that we can use all these problems very broadly in different domains of science, industry, academia, and business. But also I'm interested in not only for in these applications for the sake of these applications, but also on how to run them more efficiently on the underlying resources. And we usually work with massively parallel settings, both on-chip settings and HPC and data center slash supercomputer environments, and also harnessing different heterogeneous types of resources. Finally, the other important aspect is how to make all these types of computations high performance, scale to really large data sets, and also how to make them simple and programmable. So we also usually try to investigate how to simplify these things and how to think about them in a more straightforward manner. Another view of all these efforts is through the different layers of the computing stack, right? So if we now model an arbitrary computation using the layers of abstractions, we could identify the layer of the hardware, the layer of the networking, where we connect hardware pieces to work on something bigger together, through the middleware frameworks and runtime systems layer, up to the algorithmic layer, and also to the paradigm and programming model abstraction layer, where we reason about not only about the algorithms themselves, but also when we approach problems of the sort of how to even think about classes of algorithms. Right. And now in all these efforts, I'm trying to kind of cover this domain more or less uniformly to have deeper insights into different parts of a given problem, domain, or solution. So today it's link prediction, which is going to be one of the main components of the talk, right? So in link prediction, what we care about is, of course, being able to predict the future occurrences of some links, right? We have our graph data set. We'd like to understand whether a given link between a given pair of vertices is going to appear at some point in the future or not. Why do we care? Well, because we care about predicting future of data, right? So it simplifies the design of frameworks, it makes our life easier, it has lots of other benefits. right? And also in that particular problem we are going to discuss later, that we actually have the access to also the history of past updates, right? So we know what happened in the past with the graph. We know which edges were added or removed in the past, but also we can also have even the access to the history of vertices, right? So for example, if a vertex was added or removed. So in general, there are lots of different schemes for link prediction. And one of the ways to approach them is to identify overlaps between their neighborhoods, right? So we have now our two given vertices U and V. We want to know if there's going to be an edge between them at some point. And we can assess these chances by computing a score for this edge. And this score can be computed using different strategies. So examples are the well-known Jacquard coefficient or the common neighbors coefficient, where we basically use these neighborhoods and their overlap to detect to assess the chances for this edge to appear in the future or not. And we have tons of these other schemes out there that are basically solving the same problem. What all these schemes usually focus on are only simple dyadic edges, right? So when we compute these scores for link prediction, usually what is only considered are the simple edges in the graph, which is kind of obvious because we have a graph which consists of vertices and edges, right? But I'm going to show you that we can actually also consider more beyond these simple dyadic relationships. What I mean is, for example, triangle, which is something that which is basically an instance of what we call a higher order graph structure. So triangle is as we all know, a free cycle. Another form of such higher order entities would be a higher order neighbor. So for example, a two-hop neighbor, right? So now we have this vertex 1 and 2 that we are going to consider for the link prediction, and they may have higher order neighbors, which are neighbors that are more than a single hop away. So how do we consider now these structures, these other entities, to make our link prediction more accurate? But before we go for that, let's even ask the question, why do we even care about this higher order, about things like triangles or higher order neighbors? Well, we care about it because there have been plenty and plenty of works that show that overall higher order graph structures and using them results in really much more powerful predictions and more powerful models for many different types of graph workloads. So here I have only one citation for a quite established paper that basically uses higher order for GNNs. But there are tons and tons and tons of works that confirm this, that considering these structures is very beneficial, right? But before then we go on, let's actually take a look at what higher order even is, right? So now you have some vague idea that, okay, this can be a triangle, but let's also see what else can we find out there. Right? So in general, a very intuitive understanding of higher order is that higher order is anything that goes beyond a simple dyadic edge. So on the left part here, you can see an example simple graph that only contains dyadic edges. So there is no really higher order here. One way to introduce higher order is to introduce hyperedges, right? So in hyperedges now, in a hypergraph, we have hyperedges that are arbitrary sets of vertices, right? And we treat them as sort of edges, but we can now have interactions between more than two vertices at the same time. But then there are more ways to introduce higher orders. So one other way is to introduce so-called node tuples. So we could think of them as sort of hyperedges, but with order introduced, right? So we have also the ordering between the vertices within a given node tuple. And then we can also reason about connectivities between these tuples themselves. Another form of higher order is something we call the subgraph based higher order, where we basically come and say, okay, I also have a distinguished set of some subgraphs that I, as the user or as the developer, kind of consider here as special, and I'm going to consider them for connectivity purposes. So this is basically like a bit like hyperedges, but with some sort of internal structure on top of the hyperedges themselves. And finally, we could even think of now combining these subgraphs into tuples, right? So we now also consider the ordering of these tuples, right? So this all looks a bit crazy. I'm just showing this to basically illustrate that this higher order is a very broad term that can be used to mean many different things. You could even think of combining these notions, right? So there's actually quite common in different ways to model these representations based on these higher order structures to combine different notions. For example, combining simple edges with node tuples, or subgraphs with edges, or subgraph tuples with edges, right? So there are actually models for graph learning that use all of these different types of combinations. And in this work, we are only going to focus on basically the subgraph-based higher order notions. And if you want to learn more, basically we are going to very soon release a paper on arXiv that describes like most of these things and learning models that are based on these higher order notions, right? So this is what is coming up very soon, and this is what I meant when I mentioned that this is coming up in a couple of days. But again, we are not going to delve too much into all these details today. We are going to take a look at this link prediction problem and how can we harness some of these subgraphs and these notions for more powerful link prediction. Right, so let's maybe start with the overview of the whole pipeline architecture, right? So we would like to have a pipeline for predicting these links and their appearance based on some historical updates, right? So the pipeline at a very high level consists of 3 stages. So we have stage 1 where we need to extract the relevant higher order structures for the purpose of training and others. So we need to mine for these structures to look for them in our, for example, training graphs and extract these structures. Then we need to encode these structures in a certain way to, for example, represent them in some matrix format or other format that's friendly to our training pipeline. And finally, we'd like to conduct the prediction using these encodings of these higher order structures. So let's start with the first part where we want to mine for these structures in our graph datasets. Right, so in this mining, we have lots of challenges because now we have many of these different types of higher order structures, and we need to, and they can be actually quite complex. So one example is clicks, right? So clicks are an example way to model our higher order interactions, and we need to somehow find these clicks in certain cases. So one example algorithm for extracting these maximal clicks is the so-called Braun-Kerbosch algorithm, right? So we have a listing here, and I know it looks very complicated, but don't worry, we don't have to understand what this algorithm does. All that we need to observe is that first, it's an established algorithm for mining for a certain type of higher order structures, which in that case are maximal clicks. And that is also very complicated, right? So this is the observation that is now very important. It's a complex algorithm. It doesn't have the classical notion of iterations that we know from many types of graph analytics. It is recursive. It is very non-obvious. It comes with non-straightforward parallelism, complex memory access patterns, etc., etc. So it's very different from another established graph analytics algorithm like PageRank, where basically all we do is to iterate over all the vertices and apply the famous vertex-centric paradigm where we send some updates over outgoing edges, apply some updates from incoming edges, and we repeat this a couple of times. Right, so this is very not complicated, but when we want to mine for higher order structures, life becomes soon very complex, right? Like we're in this Braun-Kerbosch, and we have more of these problems. So we have, for example, k-click listing, we have then subgraph discovery, we have frequent subgraph mining, and all these algorithms are actually quite complex, right? So here in this first part of our whole pipeline, the goal is to construct an approach for mining, extracting different types of higher order structures using a high performance algorithm where we select what is our specific type of higher order. Right, so we need to address several issues. So basically, what are our baselines and data sets? We would like to somehow effectively develop this new efficient algorithmic baseline. We would like to effectively analyze performance and different types of metrics and so on and so on. And basically as a single solution for all these problems in the first part of our pipeline, we offer a platform called GraphMine Suite, in short, GMS. So basically, GMS is a way to extract these different types of structures from a given input graph. And it's a bit complex piece of code, but I'm not going to delve into details. What is important is to realize that this platform achieves, on one hand, ease of development of these algorithms for mining these different types of graph structures. At the same time, it achieves high performance. And the central notion for doing this are so-called set-centric, set-algebraic formulations of graph algorithms. So again, we can see the same picture as before. We have these two vertices U and V, and we have again their neighborhoods. But now what we actually observe is that these two neighborhoods form two sets. And the overlap between these two neighborhoods forms also a set. And we can get to this set, which is the overlap that we can then use, for example, to assess the scores of the link to be appearing between these two edges, is a simple set intersection operation. So that's really the central notion in that part of the whole pipeline, is that we can reason about graphs as basically sets of vertices and about graph algorithms as basically schedules of set operations that we apply to these sets of vertices. Right? So that's our abstraction, that's our paradigm here. And when we take a look now back at this Braun-Kerbosch for click mining, what we can now see is that this algorithm is basically is very rich in set operations, right? So we can see that nearly every line here, every instruction is some sort of set operation, like union, intersection, difference, or maybe comparing two sets. Right, so that's our first observation, and the contribution in that part is that using these sets and set operations as first-class citizens is the very general approach of thinking about these different types of graph mining algorithms, where we mine for different types of higher order structures. Right, so what we do here is basically we break down these complex algorithms into simple building blocks, which we can then separately optimize and code. And that means that we also make it simple. Right, so now as the developer, all you have to do is to build these algorithms using the set operations, which is usually not that complicated. And then you can, for example, parallelize it in a very, very contained manner. So we can now apply different forms of parallelism or other optimizations within a given set operation, or maybe across set operations, which on one hand makes it simple, on the other hand, it makes it high performance. So, and also you could apply different variants of set operations, right? So depending on what is the size of your sets, you could apply different variants to make it more powerful, more performant. And let's take a look at exactly what I mean here. So let's assume that we have an input set of 16 vertices, right? So we could basically, we could form this set as from 0 to 15, and this is basically our set of all the vertices in the graph. And now we have some example set, which is basically are these numbers, right? So these are some example vertices that we have in our graph. And now one way to store this physically would be to incorporate a sparse array, which is basically very simply storing all these numbers explicitly in the memory using a sparse array format. The other way to store this set is to use a dense bit vector, right? So now we could also use it as a bit vector of length n bits, where a given bit is set to 1 if the given ith element ith vector is in that set, right? So these are two ways to store a given set of vertices. And now in our example GMS graph representation, what we could do, we could apply this scheme separately to different neighborhoods, and we could now, depending on what is more advantageous for a given neighborhood, because now for some of these neighborhoods that may have many different vertices within them, we'd prefer a dense bit vector, because that's easy, then that's more storage efficient. But then for some other neighborhoods that are very sparse and don't have too many vertices, it's much better from the memory perspective to store them using sparse arrays. And you could now do it in a hybrid way by storing these things separately. So that's what we, for example, support in GMS as one specific optimization. But there is much more coming, because then what we can also do is to apply different variants of set intersection operations. For example, if we would like to run a set intersection, we could now apply different variants of these intersection algorithms depending on what are these different representations, right? So if we now store these two neighborhoods as two dense bit vectors, then we have a different algorithm that is much more powerful to be applied for that specific case, rather than if we apply set intersection on two sparse arrays. And so all these things are very easily applicable in the platform that we offer, because again of this fact that we use these set-centric formulations that are really making these things simple, right? Because now you could think, okay, now it looks very complex because now you have to deal with all these different variants, you have to manage all these different types of representations, different types of algorithms, but it's really simple because it's very modular. Because as a developer, you come and you develop your algorithm using a bunch of set operations, and then you kind of recursively may want or may not, depending on your wishes, apply these other optimizations by, for example, providing a specific variant of a set intersection that you implement in some specific way. Some performance analysis of this extraction stage is as follows. So we run different graph mining, graph extraction, or higher order extraction algorithms on our CSCS, Swiss National Supercomputing Center, the PSDAIM supercomputer, but also on the powerful single server scenario. So one goal was to show that we accelerate the state of the art, right? That if you want to extract these different types of structures, we are actually very, very fast, much faster than, for example, dedicated hand-tuned algorithms for a specific type of higher order structures. The other goal was to show that we actually simplify performance analysis of different aspects of this graph mining algorithms, right? So let's take a look at this, right? So here on this plot, we have some graph data set. In that case, it's the Nemeth24. And we compare GMS to a hand-tuned algorithm by Dasset al for mining these clicks. And we compare this in a certain metric that we call algorithmic throughput. So this is basically how many of these higher order patterns we mine per time unit, right? And that means the higher the better. So as we can see, we are much more powerful than DAS et al. And this is really because using the set abstraction enables us to make this parallelism much more effective and much simpler to program appropriately, right? Because we can now apply this parallelism within these set operations, across these set operations, and that's really what makes it more efficient when considering the mining algorithm for the whole algorithm, for the whole schedule of mining for these higher order patterns. Right, so we do achieve this goal. We have much more data, but I'm maybe going to skip that because that's a bit complicated and maybe not relevant for this talk. We have much more data because we, for example, experiment with different types of parallelization routines, schedules, and they all kind of support our claim that we come with simplicity and high performance. And then there is much more. So we do this for different types of higher order structures. You can check all these details in the associated paper. And also our website dedicated to this one part. So the paper is GraphMine Suite published at VLDB. We have also a website dedicated to this whole platform for mining for different types of graph patterns and graph higher order structures. Okay, so that's the first part of the pipeline. Again, the first very part that I know it was a bit lengthy, but go ahead.
All right, just a question before you move on to the next part, and very interesting work on like how to mine the graphs efficiently. So what's the largest size graph you have scaled to for the mining?
Oh, that heavily depends on the problem, because now, for example, now depending, so this really depends on the problem, on the higher order structure. On the higher order structure that you are using, because some higher order structures can be much simpler to like maximal click mining is basically exponential. I mean, you can at this point, right, you don't know of any better algorithm. So for that one, we used I don't really now recall the exact sizes, but I mean, we basically scaled up to the largest sizes that were up there anyway, done by the competition.
Okay.
But of course, like the largest ones that we did for the maximal clicks were much smaller than the max ones that we did, for example, for triangle counting, right? So for triangle counting, we, for example, scaled to pretty much largest graphs that you could think of that we had these days. So even there was like a very large one that we distributed across like hundreds of nodes. So that one was basically billions of edges.
Okay.
But then, I mean, you can't really do this for max clicks, right? So this really depends on the problem, I would say. And then it's even more complex because once you throw in the time dimension, then it also depends on your time dimension, right? I mean, basically one way to, but like one way to simplify this, like one approach for doing this time dimension is basically you kind of project the time dimension out, and then you basically gather all the edges that you know that appear at some point in your time dimension, right? So this is kind of giving you one way to mine for these patterns in a temporal graph. But again, this also depends on how many of these timestamps you have, how many of them you consider. So I would say there is no simple way to answer this question. It really depends on how much you have in your time dimension and what is your problem, what is your higher order structure. But I mean, the bottom line is that the framework enabled like max scalability, you know, across all the comparison baselines that we did.
Okay. Yeah.
So basically what this GraphMine Suite does, it fixes the two problems, that this extraction of these higher order structures. And this whole thing, this higher order structures is very generic, right? So you could use it, you could use it for mining dense subgraphs, you could use it for mining clicks, for mining different types of patterns. And this GraphMine Suite fixes both these problems. And if you are interested in things like, for example, subgraph isomorphism, we also provide implementations even for these non-core higher order things. We also have a bunch of implementations in the framework, right? So, but now let's take a look at how do we actually use these higher order structures for making more powerful link prediction workloads, right? So, and what we specifically care about in the HOT paper, in our HOT model, is really temporal higher order. So what do I mean with temporal higher order? So this is our example graph scenario where we have two vertices, U and V, and we would like to know if these vertices will be connected at some point in the future, right? So, and then we may have like some events, and these events, for example, could be edge insertions, right? So there may be like an edge inserted at some point later, which will be marked with a green color. And now some of these edges may actually form a higher order structure at some timestamp, right? So for example, in this timestamp here, where we inserted two new edges, we can see that there is actually a triangle forming between this new edge here and these two existing edges here, right? Then we may have more edges inserted, right? So there may be another edge inserted, or maybe even more edges inserted. Then there may be some edge removed. Some edges may be removed, right? So this is like this red dashed line here that this edges is gone, and so on and so on, right? So there may be more of these events. And what we consider in our model is to harnessing not only these higher order structures that are appearing at some timestamp, but we also consider the temporal higher order structures. So these are the higher order structures that are basically spread across the time dimension, right? So in the model, we are going to also harness triangles that may be temporal, right? So that's basically what we are doing, and you could be doing using our platform, is like mining for these patterns when you project out the time dimension, right? And basically, in depending on the data sets, such higher order structures like these triangles, if they, for example, appear between the neighbors of a given pair of vertices, it would enable us to get more accurate predictions for this link appearance between these two vertices U and V. Right. So for this, let's take a look to delve into details of the model. Let's take a look at the formal setting of what we mean with specifically dynamic link prediction. So we assume that we are using the established, very popular these days representation for these graphs, namely CTDG, which is probably the most efficient way to represent these graphs these days. So it's basically a tuple of G0 and T, where this G0 is our initial state of the graph, right? So G is our graph, and then V is the set of vertices, E is the set of edges, F and W are our features of vertices and of the edges, of the feature vectors, and this is our initial state of the graph, right? So 0 indicates that these are the initial states of these structures. And then T is the set of tuples of the form timestamp and event, right? So we need to model our events like edge insertions or vertex deletions, and we model them with these tuples timestamp of the given event and the event itself. Right, so that's the well-known way to do this. Then we assume that we have a given representation CTDG. We assume a given timestamp T, and then we assume also some edge U and V. And the question that we ask in this problem is basically, so this is like a formal way to state it, but really the intuition behind this is whether at the given timestamp T there is going to be an edge appearing while considering the history of the past updates, right? So we would like to know that at a given timestamp T there is an edge appearing between these two while considering the events in this graph before this timestamp T. So for this, we offer a hot model, which is basically this pipeline here that you can see. It looks a bit complicated, but don't worry, let me go through this step by step. Roughly, this left side corresponds to the part that we saw before, the graph mine suite, where basically, or any other method to do this, where we mine for specific higher order structures and then basically the K-hop neighbors to extract these higher order structures. The central part here corresponds to the part where we encode these higher order structures and in some specific form that is useful for making predictions. And then the final part where we make the actual predictions using some selected transformer model. Right, so this part here on the left we covered already, right? So this is where we mine for these different patterns. We mine for higher order interactions. We extract them, and we extract them using the following representation. So one of the ways that we use to represent these higher order interactions is through these matrices SV. So these matrices SV, V again is our index of one of the vertices that we care about. So the rows in this matrix correspond to a given timestamp, so to some past interaction, and then the row is basically a single past interaction at a given timestamp T, where we have some ID of the source vertex and the ID of the destination of the neighborhood vertex, right? So this is like some edge event that appears at some timestamp, right? So these S matrices are basically our historical neighborhoods of a given vertex V in that case. Right? So once we extract, so we extract these higher order interactions, we put them in these matrices, and then we move these matrices on one hand to a part where we construct the input features, right? So now we need to take these row structure, because these S matrices are still just the row structure. We need to make these things features that we can parameterize for the purpose of making the actual predictions, right? So then what we do this in the following way. So one way is to build these XVN matrices. So these XVN matrices are matrices that encode vertex features together with the information of a given vertex is a one hop neighbor or a second hop neighbor of a given vertex V, right? Because these matrices are parameterized by by the vertex V that we care about as one of the vertices to predict the link, right? So now with this vertex will have different path interactions, and we mark using one-hot encoding whether it's a one-hop interaction or whether it's a second hop interaction, or you can also generalize this easily to other k-hop interactions. We also construct using much simpler way the edge features and also time encoding, right? So we also need to provide some time encoding because we are going to use transformers which are inherently not tracking time. So we also need some time dimension here. So this is where we rely on past work for constructing these time dimensions. These time encodings, right? But at the same time, what we do, we also need to somehow, because yes, we did extract these higher order interactions, but these are at this point these are still only the information about whether a given vertex is a one-hop or two-hop or k-hop neighbor. What we also need to encode is to encode these higher order structures themselves, like for example, triangles or some cycles or something more complicated. And this we do separately in that step here, where we generate another set of matrices that encode this thing separately, right? So, and it's explicitly. So I will probably skip details here. What is important is that now we have a set of matrices that encode higher order vertex interactions, but also higher order structures explicitly themselves. Then we put these things together using something that is actually already existing. So in that part 3.4, we reuse the past model called digformer, where we apply a couple of optimizations called patching, alignment, and concatenation to sort of reduce things like memory pressure and a couple of others. So these are more like optimizations that we can apply to make these things more performant. They are not very core to the whole idea of harnessing this higher order. So I'm going to maybe skip that a bit and move from that a bit quicker. What is more important is that at some point, we took all these higher order interactions, we extracted them, we encoded them using a bunch of matrices that then we kind of stitched together, and then we put them, provide them as the input to a selected transformer model. So here our decision was to rely on transformers to basically make the predictions for these links to be appearing. And roughly speaking, you could think of a single token in this transformer as a sort of single interaction happening at some point on our timestamp line. But what is interesting though, or also a bit challenging, is that while past works relied on plain transformers or didn't really specify the details, we realized that for this thing to work together with higher order interactions, we need to find a way to relieve memory pressure. Because now, if you actually consider these higher order interactions, it will really blow up your matrices and your representations of your graph history, because your graph history now is really increased in size because you consider these higher order interactions. And like the higher k you have, and let's say the higher hop neighbors vertices you are considering, the more memory you need to do to encode this information. And this will basically blow up your attention matrix and the whole downstream pipeline that you use. And for this, our idea was to resort to a line of so-called efficient transformers, where basically there are lots of different models that are so-called efficient transformers, where they minimize the memory pressure of the attention matrix using different approaches. Right? And overall, you could think of these approaches as taking your attention matrix and applying certain sparsification scheme. And now there are many of these different schemes, and we plugged in basically something that we call block recurrent transformer. So it's one specific variant of these models where on one hand, it leverages two problems. So it solves two problems. So on one hand, it basically combines the standard attention with recurrent neural networks, but it solves both problems associated with both types of models. So for the standard attention, the problem for us here is that we have large storage requirements, right? Because we may have many tokens, because we again have this higher order structure somewhere in the pipeline encoded. But on the other hand, RNNs are very memory efficient, but at the same time, they come with low accuracy when our tokens are increasing, right? So now we want to have long timelines because we want to track our histories back into the past to a large degree, and RNNs will not really enable this, right? And here is where the BRT transformer comes in. It basically combines these two by applying sort of attention within a given recurrence cell, but to a smaller degree. So it has a smaller attention matrices, and then it combines them using basically an RNN-like chain. It's not very important for the purpose of this talk how exactly it is done, because again our approach is to kind of parameterize this by allowing really arbitrary model to be plugged in. This one worked quite well, as we can see now in some example data evaluations of some example data sets. So here we can see the MOOC data set, and we are comparing, on the left plot, we are basically comparing different baselines for different sampling strategies, right? So now we could think of different ways to sample for our edges to be used in the training, and also different metrics. So we could, for example, compare the AU scores, but also with some other scores. And so x-axis now corresponds to different comparison targets. So these are different transductive and inductive comparison targets with respect to the sampling strategies. And the bars, the colors of the bars correspond to different models applied, right? So we used here the Dickformer library, which encodes different types of models, starting from EdgeBank, finishing with TGN. And then we have HOT, which is our model here. And you can see that, for example, for that data set, we really use these higher order patterns successfully to have better accuracy in predictions for different ways of sampling our edges, right? And we also support this with additional information on the right side, where we compare what is the impact of using basically 2 hop neighbors versus only 1 hop neighbors, right? And we can see that applying these 2 hop neighbors and thus more complex, higher order structures results in basically universal improvements across different types of strategies. So we have similar results for some other data sets, but they come sometimes with slightly different patterns. So here I would like to show sort of not that great example for us. So in that not that great example, we basically show that while we are achieving also quite good performance overall, actually when we plot again these different types of higher order structures used, we can see that using more of them doesn't always help, and sometimes might be even detrimental. So that's basically one example that we conjecture. This is because there might be also some noise in these structures, right? So you might actually get more than you should have gotten when you apply mining for a lot of different types of higher order structures, and maybe you don't really want to have all of them, right? So this is an example direction of future work on what types of higher order structures are good for what types of data sets and scenarios. So more details are in the paper. So this paper basically corresponds to these 2 stages of the pipeline here, the encoding and the predictions. So this is the HOT paper that you mentioned at the very beginning. And now the final part of the talk. So what we also took a look at was that was basically something we call motive link prediction, or in general motive prediction, right? So we did this link prediction, we studied this link prediction problem, but then what we also realized was that what if we would like to predict not just single individual links, but more arbitrary structure called motives, right? Because now what you could think about, okay, I have some graph, and in this graph, I will have, different subsets of vertices, and maybe I want to know not just about single links appearing in the future, but also about arbitrary subgraphs, right? So this is, we could use such motives. So motives basically are small recurring subgraphs, so subgraphs that appear multiple times in our graph, and we use them to model molecules, gene interactions, groups of people, etc. Right? So these are basically higher order structures. But now what we are asking a question is not really how to use these higher order structures for more powerful link prediction, but now we ask the question, how about predicting these higher order structures themselves, like predicting their appearance in the future instead of just simple links? So that's what we took a look at in this one final part of this whole work that we are doing. So why is this? Is this basically also important? I mean, we can see that these motifs are a very relevant topic, right? So they have been studied over many years, but mostly in the context of how to mine for them in an efficient way. But at the same time, you can see a very renewed interest in these motifs through the so-called higher order organization. And I would like to ask the question, okay, we would like to really predict these motifs at some point in the future for our data sets, to have more robust scenarios for example, workload management, to have more robust strategies for predicting the future of our data. Right, so, but now the problem is that we don't even know how to think about this link prediction problem, because, this motive prediction problem, right? Because link prediction is well understood for, single links, right? So we have well-known concepts in the link prediction, like, for example, we have similarity-based methods, we have scores that we assign to links to assess the likelihood of their appearance, but we don't really have this defined for motives. And that's what we did in the first part of our work, like defining the whole motive prediction problem. right? And the general vision that we had was that we would like to assign some score function to motifs to make them comparable, right? Because you want to reason about, for a given set of vertices, whether there is a specific motif to appear at some point. And to reason about this, we need some score function that we can apply on a given subset of vertices. Right, so then motifs with higher scores are more probable to appear than motifs with lower scores. However, in the process of doing this, we realized that there are so many differences to link prediction. Right, so one difference is that there may be many different motifs for a fixed vertex set. Right, so in link prediction, we don't have this, because in link prediction, what we have is that, well, there are two vertices, and the link is either there or it's not there, period. It's very simple. But in motifs, well, we have now a subset of vertices, and now there may be, maybe there may be this motif appearing, or maybe some other motif appearing. And this is basically a question of how to consider all this diversity in our score functions, right? In the way to reason about this motif prediction problem. The other thing is that the incoming motifs may have already existing edges, right? So like in link prediction, we don't have this because the edge to be predicted, well, doesn't exist, right? But in motif prediction, we may have some edges that already exist and then some that don't, right? But we really care about the whole motif as a whole, and we would like to have a score for the whole thing at the same time, right? And an example for this is like groups of people, right? You may want to reason about your social network, about its future, and now some people may know each other, some maybe don't know each other, but you still want to reason about the whole groups of people at the same time to predict some patterns as appearing in the future. The third difference is that there may be so-called deal breaker edges. Like what I mean is that we may have a problem of motif prediction where we say, look, I want a motif that will have these edges, but not these edges, because, for example, these edges maybe prevent the whole motif from appearing. It sounds a bit weird, but an example would be chemical bonds. Right? Imagine you have a network of molecules and relations are chemical bonds. And now obviously the existence of some chemical bonds would prevent other, like some certain particles from appearing or maybe disappearing, right? So some of these edges can actually be our deal breakers that we know, okay, if this edge appears, a given motif will not appear definitely. And again, the question is how to consider such edges in the scoring functions, right? Again, no such equivalent in link prediction problem. And finally, the vertex labeling, right? So we may want to say that we want this specific form of star, but not this one, right? So we may actually want to kind of make our scores for the motif prediction dependent on the labeling, again, something we don't have in the link prediction problem, right? So now the first task was, okay, the second task, once we identified all these differences, was how to build this formal framework for the scoring functions for motifs and the whole problem of predicting these motifs, considering all these differences, right? So the simple starting strategy was to base the motif scores using the participating links, right? So let's say we have some given motif M, which is basically some subgraph that consists of set of vertices Vm and set of edges Em. So that's how we specify our motif of interest. And now we would say that this Em is a set of vertices that is consisting of two subsets. One are the edges, motif edges that do not yet exist. So these are the edges that we kind of collectively reason about whether they will appear or not. Excuse me. And then the other subgraph that forms this Em set are motif edges that already exist, right? So these are the ones that we already have in the graph. Right? Do you remember this example with these two edges that are existing? Right? And now, and then the score, the S, which stands for our score of a given motif, would be a simple product of the scores for all these participating edges in this motif edges that do not yet exist. So this is our simple starting strategy. For now, we don't consider these edges that already exist at all. We just assume implicitly that these edges come with score, basically with score 0, right? And now this SE is basically an any link prediction score, for example, Jacquard, which outputs some value between 0 and 1, right? So here we are basically relying on existing link prediction scores, and we just say to make a score for the motif, we take each of these links individually, and we basically multiply a selected link prediction score of these links that build the motif, right? So in that case, this could be Jacquard coefficient. Right. And again, as we do this only for the edges that do not yet exist, and that means we kind of implicitly assume that each of these edges that already exists comes with score 1, which is also intuitive because that means that if these edges exist, that sort of implicitly increase that score, right? So it's also intuitive because that means that if more edges already exist of the motif that we want to appear, we want to query about its appearance, that means that the higher chances are, I mean, the score will be higher. The more of these edges appear, the higher the score will be, right? So that's actually quite intuitive. We are normalized by construction, which is also quite nice. And then if you actually want to parameterize this concretely for Jacquard coefficient, then it would be basically like the score for a given motif would be with the Jacquard coefficient used underneath, would be something like this, right? We take the product of all the participating edges that exist and that do not exist, and we just run its Jacquard coefficient for all these edges, right? Very simple. So now what if the arrival of some of the motif links impacts the chances for other motif links to appear? Because now again, what may happen is that if there is an edge that comes up, this edge might correlate with other edges in that motif, right? Because remember, these motifs are subgraphs, so they contain more edges, and now there may be correlations between these edges, right? So this is what we add with a generalization of this formulation. So now we basically say that a given score for a motif is modeled as some dot product of a vector that models the scores of these individual edges times some other vector of weights that is kind of the user knowledge in the domain. Because now these correlations will heavily depend on the domain knowledge, and we model this with this vector W of coefficients. Right. What is important is this is going to be a convex combination of the vector of the link prediction scores here. So we now take these individual link prediction scheme scores, we sort of combine them using this convex combination, and we get some final outcome, which is now going to be more general than what we saw before, right? And in the extreme case, we may have these deal breaker edges, right? Because now some correlations may be actually very, very negative in a way that some links that come may be impacting the chance, maybe reducing the chance for the motif to appear to 0. This we basically model with extending this set EM with another set of these deal breaker edges that we know, okay, we don't want these edges to appear. And this could be, for example, these two edges here. We mark them with red. We don't want these edges to appear. They are in this other set EMD. And now we again model this with this convex combination, but now we just add a bit more massaging here. Basically, we said that the deal breaker edge would come with a negative score, right? So a given deal breaker edge that again is not there but may appear there is coming with a negative score of this given link. A deal breaker edge that does exist already, which means that there is no chances for this motif to appear at all, is just 0, right? And that means that the whole score will be 0, right? And here you can see that the final formulation basically is a product of all these edges that are non-deal breaker ones with the products of these scores for all the edges that are deal breakers, but then we take 1 minus these scores, and this means that if there is a deal breaker, this is 0, and effectively the whole thing is also 0. Right, so now in our paper, we have details about all these heuristics that we consider, like Jacquard, common neighbors, and many others. You can check all of them in the paper. But what we did, so this is kind of less interesting, but what we did in the paper was basically trying to see if we could also, besides heuristics, use some learning approach for this motif prediction. So here we kind of based on the previous works that showed that we could use learning approaches for link prediction, and we also wanted to show if for the motif prediction we could also use learning strategy. So now before we continue, let's quickly take a look at the basics of the learning, like the general deep learning that we applied. I mean, this is something that we all know, but I'm going to still go through it just to avoid any misunderstandings or confusions, right? So in general deep learning pipelines, we have like a set of samples that we use to, like for example, pictures of animals, and then we are using a given sample to run some inference, like move the data through the forward in the forward pass through our network. We obtain some predictions. We compare them to the ground truth. We backpropagate and we update our parameters, and then we repeat this many times to train our model. Right? We learn a heuristic in that way. And now we apply this very, I mean, the obvious general approach to our motif prediction problem, right? And how we do it is as follows. So the goal is to predict this motif F. We would like to predict this for a given set of vertices, right? So we select a set of vertices. We say, okay, I want to know if a given motif will appear. Right, so this is our fixed set of vertices here. So now we need two types of samples to train our model, right? We need positive samples to train the model. Okay, these are these are the existing motifs that already exist, and this is basically how they look like or how their neighborhoods look like. And you should kind of learn this as the positive samples, right? So we mine for this positive sample. So this is again the extraction problem. The first part is the pipeline where we extract these higher order patterns. This time for the purpose of using them as basically prediction training targets, right? So we mine both these motifs and their neighborhoods, right? Because we also want to know for a given positive motif sample, what is the neighborhood to be able to predict correctly these motifs based on novel neighborhoods, right? We also mine for negative samples, which are basically like other motifs that are not like this one that we care about, right? So these are our negative samples. We can mine for them together with their neighborhoods, right? So and then what we do is in this pipeline just replace our input samples with these mined motifs, and we replace the picture in question with a given fixed set of vertices. And our question on our for example, training target is, for example, will a given k-click appear or not? Right, so, and we use these samples to train a neural network model. So here we rely also on past work. We basically took a model called DGCNN. We modified this model to reflect these changes, to reflect basically the fact that we care about motif prediction. And we use this model as the basis of the pipeline of the modeling and evaluation and the training pipeline we call SIM. So SIM is the acronym for learning from subgraphs, embeddings, and attributes for motif prediction, right? And in this pipeline, in step number 1, we specify the vertex set and the motif to be predicted. So again, what vertex set is the one we care about. We specify the motif. So this is again what connections, what higher order structure we care about in this prediction problem. Then we mine for these positive negative samples. So that's what we just saw. We look for them. We use our extraction tools to find them. We also extract the subgraphs around these samples to also have the neighborhoods considered in the training pipeline. Then we construct some embeddings because we need to feed this data, the structural data into the model. So we need some embeddings. So this is where we construct the embeddings. We label nodes we also use some labeling to have a specific way of considering the specific types of numberings. That's also what we need. We create the final feature matrices, and basically it's a bit complex, but what we do in this whole pipeline is just to again extract these specific subgraphs that we now care about as the prediction targets. We construct their embeddings and their feature representations, and then we just use these feature representations to train the model for the purpose of motif prediction problem, right? And what is more important is what types of higher order structures we consider. So here we consider both very sparse ones like k-stars, but also very dense ones like k-clicks, and basically anything in between. So we parameterize also the pipeline by what are the types of what is the sparsity/density of the higher order structures, and we can basically pick arbitrary ones. Right? We consider both transductive and inductive scenarios, which like the transductive means that we pick a motif in a given graph A, and we train for predicting instances of this motif in the same graph A. Right? And we also use inductive scenario where we pick motifs in some graphs A, B, and we train for new instances, for predicting new instances of these motifs in these graphs A and B. Right? So the graph that we use for prediction, for the testing, may be different from the graph that we use for the training. Some example data. So I think we don't have much time left, but I will just go very quickly through these numbers. So in this data, what we can see here is that on the x-axis, we can see different higher order patterns that we now care about as the prediction targets, right? So we would like to know if, for example, a 3-star appears or 5-click appears, or 3dB star, and 3dB star is basically a star with some deal breaker edges, right? So these are the deal breaker edges. We also consider them in the evaluation. And now the rows in this matrix are different comparison baselines. So these are, for example, heuristics. So this is common neighbors heuristic, or atomic adder heuristic, or Jacquard coefficient heuristic, or the seal, where the seal is basically this learning-based approach for predicting links, right? So all these things are these link prediction schemes that we kind of collectively use to predict a given motif. And then these Malmin and AVG are different ways to aggregate links, right? So we have even more comparison targets by varying the way in which we combine these heuristics for links. And what is really important is that our architecture, which is these 2 final rows. So this is the SIM and no embedding and SIM. So these are some variants of the SIM that is not very that relevant. what is really relevant is to see that on one hand, we outperform all these other schemes in the accuracy, but the more important notion here is actually something more interesting, is that for all these other schemes, if we take a look at this x-axis, we can see that we kind of compare increasing complexities of motifs, right? So we take the 3-star, then we take the 5-star, then we take the 7-star. So this is basically where the motif gets more and more complex, right? Then we do the same for 3-click, 5-click, 7-click, right? So it's like a simple triangle, that's a 5-click. So this is again increasing complexity of a single motif. And the same here. This is the same thing here, right? We also increase the complexity of the star with these deal breaker edges. And now all these other schemes, they sort of, their accuracy is sort of either staying sort of constant, but also very low, or it's decreasing as we increase the complexity of this motif to be predicted, right? So for example, for the SEAL, the learning-based approach, like the accuracy is decreasing, is getting smaller and smaller as we make the comparison target more and more complex. But for SIEM, we actually usually improve the accuracy. So the more complex motif is, the better we are. And that's really because we consider explicitly these correlations between the links, right? So now the more complex motif to appear, the more potential correlations between these participating links may be. And we consider them explicitly the training. And that's why we are basically getting better, because for us, these correlations are the source of more information in the final prediction scores. Right? So we have much more results in sensitivity analysis in the paper. And more details are in the separate paper called Motif Prediction with Graph Neural Networks. So that's it. Thank you for your attention. And now I'll be taking any questions that you may have.
Yeah, so thanks so much for the excellent presentation. So if anyone from the audience have any questions, feel free to just unmute yourself and ask. Yeah, so I think it's very interesting work like on the motif. So how do you do the evaluation actually? Do you pick random set of other nodes that don't have this motif and you do a positive, or you do a like, so how does it compare?
I mean, so what we are saying now specifically is how do we select the samples, right? So here, like for the positive sample, we just select, you know, we mine for the ones that we care about. So this is like a simple thing. For the negative samples, we select different ones. So we have a couple of different sub-strategies for these negative samples, and it's basically like one of these. I would need to double check the paper now, but one of these sub-strategies is like simple randomized selection. So we just randomly select pairs of vertices, and then we have some motifs that are usually not like the motif that we care about. But then we have also, but this is like a simple thing for selecting negative samples, and also this was kind of this was also shown in the dynamic link prediction scenario, that when you build these models for predicting patterns for link prediction, you don't want just to have this random sampling, but you also want some more complex ways, right? And we do the same here. So in the motif prediction case, we also have, for example, negative samples that are almost like the ones that you care about, but not completely. And for this, we are mining for the motifs, and then we, for example, change randomly some participating links of these motifs to get, you know, negative samples that are resembling what we care about, but not really, right? So we have a couple of these sub-strategies how to select negative samples of these motifs. And by the way, we do the same for link prediction in this temporal dimension, right? So for the link prediction in the temporal dimension in the HOT model, we also use a couple of different strategies for selecting negative samples. Like we also randomly select the links, but we also select, you know, links considering whether a given link appeared in the parse and then disappeared, or things like that.
Yeah. So, yeah. So thanks on the great work. There's a question from the audience.
Yeah, go ahead.
Could you please comment a bit more on seam versus seam with no embedding?
Oh, so it's basically hold on. I mean, basically what this is like an optimization where we sort of provide more, we kind of, in the seam without embeddings, we only mine for these samples, and then we basically encode these samples without more information. So this is like seam without embeddings, and then seam with embeddings is a bit misleading name. I mean, I think it's not the greatest name, but in the seam with embeddings, what we do, we perform additional structural, we impose additional structural information into the matrices that we use to encode the sample. So basically, we run things like node2vec and deep walk to construct some additional structural information for a given sample and then add it together so that we have more structure considered in for a given motif sample. So that's basically what it means. So that's either without this additional structural information or with this additional structural information encoded in some way.
I see. Yeah, that makes sense. Hope that answers your question in the audience. Okay. Yeah, sounds good. Yeah, so thank you so much for the presentation, and we can wrap up here. And
yep, thanks as well for having me, and
thank you.
And yeah, thanks again, and talk to you later, probably via email. See you, bye.
Yeah, thank you. See you.
Bye-bye.
Bye.